Perfect. Welcome to the NDC Copenhagen Sweatbox. Um, if you need to strip down to your shorts, get refreshments, take a break, don't, but I wouldn't be offended. So I am David, and I want to talk to you about this really weird through line in technology. I love finding all the weird through lines in technology that runs from a bunch of kids at MIT in the 1980s through John Carmack, all the way through to Fortnite in the 2020s, and really about how people's creative urge to make things with just about anything they can find always seems to succeed. So there's a lot of code in this talk, a lot of code, Scylla. And there'll be links at the end, so if you miss a bit, don't worry. If it's a bit too small, yell at me and then don't worry. So we're going to get to building game engines from scratch in a browser in a little while. But first I want to tell you a bit of a story about the first ever video game mod. Now, quick question. Anyone ever modded a video game? Okay, so great. So in 1981, a couple of MIT students named Doug McRae and Kevin Curran started a company called General Computers. Great company name. And they released their first game, and it was called Super Missile Attack. Now, what was really interesting about Super Missile Attack is that it was an unofficial sequel to the arcade game Missile Command. And the two students have programmed the game by building an arcade modification, like a hardware hack. So they built a board that you could physically attach to the original Missile Command arcade cabinet, rewire some of the circuitry, and it would make the game harder. Now, they followed this up by building a game called Crazy Otto, using a similar technique to modify Pac-Man. Then they modified arcade cabinets again, and they accidentally invented game modding. Now, what the mods did is they took the original arcade PCBs and they added a few new features, mostly to increase the difficulty. Because you've got to remember, in 1981, there were like 10 games. So for their part, Atari obviously tried to sue them out of business. And instead, actually, they ended up hiring them and coming up with a settlement. And as part of their settlement, with Atari, they agreed never to sell unlicensed mods again, like Scout's Honor. Which is funny, because a lot of people in this room might have played Crazy Otto, because what actually happened is they sold Crazy Otto to Midway, who changed the sprite and released it as Mrs. Pac-Man. So the first ever game, well, the second ever game mod, technically became a product. So I find this really fascinating because they were probably the first people to get into games in the way that most people probably get into games today, which is basically screwing around with something that they had on their computer as a kid, and through modding games and using, now, general-purpose game engines. In fact, that trend of modifying arcade cabinets persisted all the way through to the late 80s and early 90s. So my other really favorite example of this was this game here. So unless you were born in about 1980, you probably never played Street Fighter II Rainbow Edition. Not really one that ever comes up. But it was a hack to an arcade cabinet in Japan that was so popular that it made more money in 1992 than the original Street Fighter II game. And eventually Capcom cloned the hack, and they released it as Street Fighter II Champion Edition on the Mega Drive and SNES. So literally a fan favorite version of the game came from someone screwing around with the rules. Now, it's interesting because early gaming especially was super self-contained. So each game you made required kind of mastery of the target platform and its hardware and the gameplay logic and the rendering code. It was all intertwined. These were just programs for specific machines. And if you look at game ports at the time, you can see that, because early game ports weren't really ports at all. They were just complete re-implementations of the game by looking at one of them and trying to recode it on another piece of hardware, normally by different people. You know, those games, Paperboy is famously a very ported example of a game that is different on every platform and bad on many of them. And as games got more and more complex, bigger businesses and organizations, motivated by getting to market quicker, because capitalism gonna capitalism, started building games on top of their previous completed games to speed up development. And there were really weird little anomalies here. Now, I don't know, did anyone know this? That Super Mario Land, Super Mario Brothers, even on the NES, was built on the code base of Excitebike that came out the year before, because Mario's locomotion is the same as Excitebike's movement code. So super interesting history of this. And as the 80s kind of progressed, lots and lots of companies started building internal game development toolkits and shared code bases. So this led through kind of the late 80s and the early 90s into this boom of what were marketed at the time as game creation kits. So some of them were private. You've got things like the wonderfully named Scum engine, which anyone that's played a LucasArts point-and-click adventure will have used. Scum, of course, stood for the script creation utility for Maniac Mansion. And other creation kits actually started to be launched as commercial products rather than game dev tools for companies. So when I was a kid in the early 90s, I remembered using Click and Play, which is like a GUI drag-and-drop thing to make little games. But Gary Kitchen's Game Maker was probably the first commercial kit that hit the market in 1985. Other popular things, you may have heard of RPG Maker. RPG Maker celebrating its 30th year this year, making kind of indie role-playing games that get ported to everything. So while game engines didn't exist in their traditional format, everyone was trying to work out the answer to the same problem. How do we generalize bits of code and build new games without having to rebuild everything from scratch every time? So every talk on video games ever leads to Quake, I think, is basically the truth. And everything changed mostly when id released Doom. And I feel like I literally have 3 talks that are just like, Doom's really great, you should play Doom, it's really important. So in 1993, Doom popularized the idea of user-created game mods for the first time, specifically spurred on by map making, because Doom's network multiplayer was such a big hit, people wanted to play maps that other people had made. There was a little bit of commercial licensing of the Doom code base at the time, so notably to Raven Software, who made Heretic. I believe Raven are now still working in the Call of Duty mines. They also built Heretic on top of it, which was produced by id Software's John Romero, and Hexen after then. So Raven ended up modifying the Doom code base to extend its features, right? And this kind of gave id Software that little spark of an idea, because there was a business model here. So they followed up Doom with Quake, which introduced the more than a level editor driven mods, like this idea of total conversions. So they introduced something called Quake C, which was a dialect of the C programming language, noteworthy to me personally because it's why I wanted to learn C when I was a kid. And it was kind of built as this extensibility point, a compiled language based on C, but designed specifically to interact with Quake. Now, at that time, id started licensing the Quake engine to other companies. So notably Valve Software, who made Half-Life in 1998. So they modified the Quake code base, which they referred to it as the gold source, literally because id gave them a gold CD with a folder on it called source, and that's why the source engine is called source. It's weird. And then finally, obviously, Epic turned up, and they introduced Unreal and the Unreal Engine when they were still wonderfully called Epic Mega Games, which is an excellent company name. So that was kind of 1998, and they followed id's licensing model and started licensing their own, at the time, very impressive 3D engine, which was the engine that powered Unreal. Now, it's mostly lost to history, but Ken Silverman built the Build engine, which was actually called the Build engine, in 1995 to power Duke Nukem 3D, which came out the next year. And it's not clear when the word game engine emerged, but I think it was probably id adopting Silverman's word engine when they were getting into the licensing business. And by the time Epic turned up, the word engine was then kind of popular. So, much of the terminology that we have to describe all of these legacy engines actually was retrofitted onto them after the fact. And actually, the late 90s and early 2000s led to this explosion of reusable game engines as all the big technology publishers started building their own in-house engines or licensing engines to start building their own franchise games on. And for a long time, both the Quake engine, which is now called id Tech, and the Unreal Engine, which is still called the Unreal Engine, were the two kind of warring technology code bases. So I think it's kind of amazing, actually, that the Unreal Engine today has a version lineage that goes back to 1998. So let's talk about what game engine actually is. And it's funny because you see lots of discourse on the internet where people hate on game engines, and what they're really talking about is things like what the graphics look like, which is not really a game engine. So I guess for a web audience, game engines are the web frameworks of video game development is the obvious shorthand. So they're frameworks that provide a programming model for you to build games on, and they tend to come with lots of optional libraries and modules that are capable of like really diverse ranges of things. And often they tend to provide an opinionated programming model of how they think a game should be constructed. So they'll usually come with modules for things like rendering graphics and handling input and audio and game logic and AI systems and data streaming and all these kind of capabilities that you see in this chart up here. Now, engines are obviously, because of this, quite modular and tend to be customized by licensees or people that are building games in them and extended to do kind of unique things in specific games. Now, on top of all of this, engines are often useful just because as long as the engine code you're using is ported to different platforms, your game will probably run, right? And that's cool from a kind of a business perspective. So for reasons that we will get into later, I ended up building a game engine that runs in web browsers over a period of about 10 days a couple of years ago. So what I want to do is I want to use some of these techniques as examples to show you how some of these subsystems are created and hold together. So obligatory caveat before we start, there are many valid designs for game engines. This is just one of them. These are some representative implementations. They're not exhaustive. If I was being exhaustive, you'd probably be here for a 3-year degree. Consider this an introduction to the concepts, not the code to copy and paste into your cool new game. I say that with a bit of a side eye to the YouTube people who will probably complain about this later. So I want to start off with one of the most core concepts of most real-time game engines, a game loop. So while not all games run in a loop, most real-time games do. And the game loop tends to run at a fixed tick rate or update rate, depending on which engine you're talking about. And what that does is it coordinates the execution of all of the other subsystems in a game engine. So they tend to do things like poll for user input, increment AI, execute user-defined game code, and they step forward the game every tick. Now, traditionally, a game loop would have run at a fixed refresh rate, but over time, a lot of engines have decoupled the internal tick rate of the game from the rendering systems. This is specifically because if you've ever taken a really old game and tried to run it on modern hardware that runs it really, really quickly, that tick rate is accelerated because the refresh rate of the screen generally was coupled to the game. Now, renderers, or rendering engines, what they do is they take the game state, whatever the bag of data that the game operates on is, and they generate visuals to a game. Now, 2D renderers are generally concerned with render ordering, sprite animations, camera positioning, and post-processing effects. Now, conversely, 3D renderers tend to deal with things like 3D asset loading pipelines and data streaming and texture mapping, and usually scheduling calls to GPU implementations for things like pixel shaders and fancy graphical effects. And renderers tend to support different low-level graphics APIs, so you might have heard of the obvious ones like DirectX and Vulkan and OpenGL, or Apple's Metal, which I'm sure somebody uses. But they all support different physical target platforms. And then finally, I want to talk about scenes as a concept for organization. Now, not all game engines have scenes, but a lot of the engines you see today, notably things like Unity, use a scene metaphor, where a scene is a high-level abstraction over the kind of thing that the game is doing at the time. So maybe you have your first-person scene where you're navigating the world, or an inventory management scene, or a mini-game scene, or a main menu and options scene. It's a way to collect different categories of kind of subsections of your game. And generally, a scene will describe behaviors and contains objects or NPCs or game world elements. So, to bring some of these concepts to life, I want to take a look at the admittedly slightly over-designed version of Conway's Game of Life. So, I don't know if you've heard of this game before, but it's basically meant to simulate life. It's a simple cellular automation game that was designed by a mathematician called John Conway in the 70s. Now, the reason this is interesting in the discussion of games is it was technically designed to be a zero-player game, where its initial state requiring no further input, and then the rules of the game get applied to it, and it will mutate over time until the game finishes. Now, the game of life takes place on a 2D grid, where each grid location can either be alive or dead, and every time the game updates, the cells around the board change state. So the rules are very simple. Any living cell with two live neighbors dies, as if by underpopulation. Any cell with 2 or 3 neighbors lives on to the next generation, and any living cell with 3 or more neighbors dies because of overpopulation. Finally, any cell with exactly 3 neighbors comes alive. So we've got this kind of state machine thing. So I want to break this down in a little bit of code, which, God, that's going to be tough to read. Excellent. I hope we brought our theatre binoculars. So we're going to define a really minimal possible engine. So this is the smallest game engine I could possibly imagine, which is why it's in a small font, clearly. Now, our game engine contains basically an instance of an iRenderer and an iScene, 2 interfaces. Now, the scene can be set from the external calling code, and then we've implemented a game loop, literally just a tick that refreshes every step through the game. Now, our game loop calls an update function on the scene, and it calls an update function on the renderer, and that's all we're doing, right? So we just got this thing that ticks forwards. We do it every 100 milliseconds using an API in the browser called request animation frame, which is like a battery-efficient stepping frame. Now, we need a little bit of startup code. So I made a HTML file that calls the JavaScript file and passes it a canvas, right? So our startup code is going to create what I've called a canvas renderer and the game engine that you just saw. And then we set the game of life scene as the thing that the engine is running. So really, really simple kind of framework level execution code. Now, you don't have to read this. This is meant to be small. Our game of life scene implements the iScene interface. So it has an init, and an update, and a render function. And the code in the middle is just those rules that we're just counting the cells around each element in the grid, and we're flipping them to either alive or dead. So it's not interesting what it really does. So if we zoom in on that update function, there the rules are. Now, please don't try and read that. But the most important thing is it takes a snapshot at the start, iterates over the cells, flips the flags, and sets the new world state on the way out. So we've got this kind of every tick operation. And then in our render call, I'm going to show you that the greatest rendering engine you have ever seen in your entire life, it draws squares. All it can do is draw squares. It's great. It's perfect. Why would you need anything more? So in our render call, we just loop through our cells, and we draw a black cell or a teal cell, depending on whether the cell is alive or dead. It's dumb, but it works, right? And this is the code of our glorious canvas renderer. And all I'm really doing here is wrapping the browser's basic API for drawing. So you might notice there's one interesting thing here where we are flipping the y-axis in 2D space, because when you're in a browser, 0, is top left, and when you're in a game world, 0, is bottom left. So we're just doing a little bit of maths there to make sure everything looks right, and it won't affect this example. You wouldn't even notice, but it will later. And it works. And we can run it, and it's cool, and there you go. You can all leave now. Single-player game engine, 0 interaction. You got this. No, it's cool. Obviously, you could write a game of life implementation in about that much code, and you don't need all the kind of over-design of an engine and a renderer and all those abstractions. But it's a really good example of what that core looping element of most modern games looks like. So, while watching the game of life play out in its 0-player existence over and over is the most fun I personally can possibly imagine, I think most people want a little bit more from their games. So I want to talk about input handling a little bit. So input handling subsystems are used to convert input from things like gamepads and mice and keyboards through what we would call a key map or a button map into desired game actions, so kind of requests for changes in the game world that you can pass around the game. This is useful because it allows you to kind of both decouple input from action and allows people to override key bindings, which is great for accessibility and all the esports masters looking to beat your key bindings. So we're going to need a game to rip off for our next example after we ripped off the game of life. And there's an excellent little indie platform game that started life as a Flash game in the 2010s called Thomas Was Alone. Now, it's a game about a computer mainframe going wild and malfunctioning AI, and you should probably play it. It's really cool. But most importantly, all of its characters are just various square objects that you can see playing in the video there. So we're going to make our own version of this game. I'm going to call it David Was Alone, and we're going to start with input handling. So this should be a bit bigger, even if the contrast is bad, because it's beautiful in here. Building on our own glorious Game of Life engine, we're going to add a new interface, an I input device for our engine. Now, the input device implementations are going to be responsible for mapping input to an object containing the currently requested game actions. Now, thankfully, modern web browsers are really good at this, and they can deal with about any form of input by default. So that includes gamepads, touch, and obviously mouse and keyboard. So here what we're doing is we're updating our engine to keep track of a connected input device in an array. And then we're going to modify our game loop to pass this collection of input devices to our scene on each update scan, so the scene can call into this interface and see what game actions the user has requested. Finally, obviously exposing a function for our startup code to connect input devices. So this is our keyboard class. You don't need, again, to read it carefully. What we're doing is we're just wrapping the browser's event listener on key down and on key up. And what we're doing is we're keeping track of which button is pressed in a set so we can query it inside of our scene. So when getCurrentActions is called, what we do is we return this actions object, which sets states for left and right and jump, all the things you need for a modern video game. And you can see here, again, you don't need to read it, the gamepad API isn't much more complicated. All we're really doing is detecting USB connection events and keeping track of a gamepad ID. And what this does is it allows us to use a D-pad on any standard Xbox or PlayStation controller connected via USB. The browser just supports this stuff, super awesome. So we're keeping track of which gamepad is connected and querying its button state on line 26 at the bottom there. And then finally, in our level scene, we can flatten all the controller inputs down. So there's a bit of a reduce here that checks the state of each button. And then we can move all of our hard-coded player character object when a valid game action is requested. So luckily, David Was Alone is entirely made up of squares, so our existing renderer is perfect for the job, and I can draw a glorious square, and it works fine, and it's perfect. So up in the top corner, you can see where we changed the index page, and what we've done is we've added our keyboard and controller inputs by calling that connect input devices function. So David might be able to move, but he's defying gravity, and he's still very, very alone. And all we're doing here really is just moving a square, just an X or Y coordinate, and that gets rendered on a canvas which is reset to white on every loop. So it's not really a character with any behaviors. It's just really two coordinates and a square that we're moving. So let's make that a bit more sophisticated. Now, at the moment, we don't really have a player character in our game. Game engines generally keep track of what we call entities, and just like in any other kind of program, an entity is at the very least a collection of data, sometimes stored alongside the behavior in kind of a traditional OO model. Now, building game entities for behavior helps us keep all of our logic out of the main scene and organize our code better. It's literally just a structural organization pattern for game dev. And to add the concept of entities to our code base, what we're going to do is we're going to firstly create a new draw function in our renderer. This will keep all the display logic abstracted from the core of the game operations. And then what we're going to do is we're going to add a few new interfaces, something called iUpdatable, that describes anything at all in the game world that can be updated when the game ticks. And then a game entity that has a physical location in the game world. So that just means an X and a Y and a width and a height, which itself is then updatable. And you can kind of see where I'm going here, right? We can move all of our logic from updating our player into this new player character entity, and that generalizes our level scene more, which is now just responsible for calling update on every single entity that it's keeping track with that's stored inside the scene. And while it might feel like we're just moving code around, this basically means that we can now add other kinds of entities to the scene that all tick and all get rendered by the renderer. Now, another really common approach in game development is to implement something called entity component systems. So the language here is a little bit tricky because everything in programming means three things. So let's talk about the terminology, right? So in a traditional object-oriented design, data is co-located with the functions that apply to it. So commonly modeled as classes in most of your programming languages. Now, games in the late 90s, notably if anyone remembers Thief, the Dark Ages, they pioneered this idea of entity component systems, though the name didn't exist at the time. And they were almost the opposite of OO, where the data and the state of the system doesn't contain the behaviors at all. It's just the raw structured data. And there's a registration table of some kind, now it depends on the engine as to how this is implemented, that ties that data to the various systems that apply to that data, called components in this analogy. And then every tick, those systems run and get handed the data that is registered for them, and they increment the state. Now, this changes our relationship from updating each object in memory to running the AI system and process the logic, run the rendering system, run the movement, run the game logic. So it's a little bit like a visitor pattern, if you've ever implemented one of those in like standard development. Now, inspired by this, though not explicitly in ECS, in the 2D engines I built, I like the idea of introducing this concept of characteristics. So attributes that entities can maintain a subscription to that can be used by multiple entities in the game world. So, for example, both the player and enemies can be physics objects that gravity applies to. Maybe something can be killable or jumpable. So I like using the word characteristics or behaviors because it avoids this often overloaded component language used in ECS, because like component means about 30 things I can think of. So to adapt our engine, we've added an update context that contains our game state to be passed around on each update of the game loop, and we've modified our game entity to contain an array of characteristics that are themselves updatable. Now, of course, we added a very simple interface for characteristics to implement where they can execute logic as well. Kind of big enough. Now, our level scene is now responsible for just triggering the update function of any characteristics that our entities happen to have applied to them, and then optionally calling update if there's any further logic that's contained inside of our entities. So we've got these two different places to put logic, stuff for just that entity, and stuff that applies to lots of different entities, which gives us a nice way to do kind of composition over inheritance reuse. So it slims down our entity class to a minimum. Right? So one of the nice things about generalizing these behaviors is that you can take one system and apply it to lots of different kinds of entities. And you'll notice in this example, I'm just adding an instance of the characteristic to an array, rather than using like a registration table that we resolve at runtime, mostly because it's just easier for a small example. Now, while moving our existing behavior into an ECS-like structure might make our code look a little bit neater, it also has prepared us for adding physics to the toy engine, because having physics apply to something can be implemented as a characteristic. So physics simulations are complicated, and I can't do maths, and they're hard, and being realistic makes them not fun, and basically they all suck. So for a 2D platforming game, we're just going to do Mario physics. Right? Mario physics is easy. So first, to do Mario physics, we need to rework how we implement our controls. So rather than just kind of forcefully moving a square left and right, we're going to set a velocity, right? So something gets faster and gets slower. And we're going to add some variables to store the current object x and y and velocity, and define a bit of a weight, which will help us implement jumping and falling, and also a flag to tell if we're jumping. Now, we've set these values in our player character class, but we're also adding a new physics object characteristic after the existing controllable one that lets us move our square around. So next, all we're going to do is we're going to go back to that controllable characteristic, and instead of setting a value, we're going to instead increment or decrement our velocity when keys are pressed up to a maximum cap. And we're also going to add support for jumping by setting a velocity y value when someone requests that jump action. So now finally we can implement our physics object characteristic. Now I'm not going to reproduce the entire kind of characteristic here, but I want to call out a few important things. Firstly, we're going to calculate some collision points that line the bottom pixels and the middle point of our box. Now this is important because it gives you collision detection, both a solid way to find the ground. You see if anything at that bottom is touching the floor. But also it's a little bit of it gives you a little bit of give when you're colliding during jumps. Because what you don't want to play in a 2D platform game is a game where every time you bang your head on the top of a platform, you fall to the floor again, right? You like a little bit of overlap and a little bit of nice, gentle give. And then finally, we apply gravity, right? And we're going to implement jumping by splitting the amount of time it should take for our object to fall by our 60 frames a second frame rate, and just slowly decrease the upwards velocity of our character until it reaches 0. And then the physics code that makes the character fall again until it reaches the floor will just take into effect. So combine those two things. We have a control that sets the velocity, which means when someone presses a jump key, they will first move upwards, and then they will slowly slow down and fall in an arc, like Mario. It's kind of pleasing. So actually implementing the falling is done when we calculate gravity, right? So a speed that the entity will fall per game update is set. And if they're never not on solid ground, we just move them downwards, increasing the speed until they reach a terminal velocity for their weight. Now, after adjusting our x and y velocities, we apply movement to the entity to shift it to the next location in the screen. So this is just happening every single tick. And this is what our game engine and our scene files look like at this point. He can fall, David can jump, but he's definitely still alone. So, anyone heard of Blue Peter? Who's British in the room? Okay, perfect. Now, in the UK, we have this kids' TV show called Blue Peter. It's the longest-running kids' TV show in the world, and they frequently show you how to build things out of kind of paper cups and bits of cardboard, and they have this great popular phrase. Here's one I made earlier. Now, if you will allow me a bit of a Blue Peter moment here, I'm going to switch gears as we move to our next example. So a couple of years ago, during preparation for a conference booth, I spent a furious 10 days building a 2D game engine that could run in a web browser. Now, the idea was that attendees could walk by and play the game, completing asynchronously with everyone else that day in like a Mario Kart-inspired ghost race against themselves. It was quite fun. It had to run on a booth on mobile phones and work with controllers and not suck. So as we move on to talking about graphics, I'd like to introduce you to the magnum opus that is I Am Jam, the game where you, a humble orange, try to become jam. So here's the one we made earlier. So while I was working on the nuts and bolts of this game engine to make all this stuff hang together, Joe, who's sitting in the front here, who was working on all of this gorgeous pixel art to make the thing actually come to life and work. I can't do this. That's a lot of pixels. So other than how good they all look, there's nothing special about the graphics here. You know, there's a couple of JPEGs for background art, some keyframes for enemy mice that try to eat our intrepid orange, and some kind of cute clutter objects. Now we need to get these into our game engine so we can draw more than just squares, right? So this is why we need sprites. So sprites are animation sheets made up several images that get played like an animation. They're like a digital version of a flip book that you would draw as a kid. So much like our earlier player character entity, in the code base for I Am Jam, we had to design an entity that keeps track of the animation frames so we can increment them correctly to animate as the game plays out, step them forwards. So our game used two conventions. We supported animated GIFs, which we would write to our canvas element in the browser directly. And it supported a series of images that we could load sequentially and sequence them and pack them together. Now, 2D engines tend to use either flat files, which is something that gets called sprite sheets often, which are normally one big image with an offset that you chunk through, normally in a line, and you just kind of shift the offset as you read them like a flip book. But in our case, we just had a load of single files on the disk that we loaded from a web server because we've got like 20 images. Now, this is the character class for I Am Jam. It's a touch busier than the one from David Was Alone. And we have two sprites associated with our character, so there's only really the bit at the bottom that's important. Our character class initializes its sprite when it loads, and each time the game updates, we called it tick here. It calls tick on the sprite, and the sprite chooses whether it needs to step its frame forwards. Now, our drawing logic is also a little bit more complicated because of the character state. You've got to check if they're standing still, or they're moving, or they're jumping, because you want to pick a specific frame when they're doing those things. But once we work out if we're alive or dead, and if we're moving or not, we just call draw, and the sprite function does the heavy lifting to select the appropriate image to draw to the canvas. Now, the sprite class is responsible for loading all the frames in a sequence. And the other thing it has to do is it has to create flipped versions of the sprites when things run left to right and right to left. So we do a little bit of image processing, done with the confusingly named but still awesome libgif. So every 5 updates to the game, the frame counter will proceed, and then when the sprite class is asked to draw, it will draw the next frame and draw the next frame. Now this class is responsible for drawing the image onto our canvas directly because the renderer in IMJam is a little bit different from our previous example. And it works. Beautiful mice. Has anyone ever said that? So, in a 2D game, layers are rendered on top of each other to create this sense of depth, right? And you'll see this in all the classics, you know, your Sonics with your parallax scrolling and your Marios where you can run behind things. So what tends to happen is visual elements are ordered from back to front, kind of like using a Photoshop layer. We have the background layer, which is the furthest layer away from the viewer that normally contains static images that set the scene. Sometimes you'll have a couple of backgrounds that scroll. You have the middle ground layer that tends to add elements that are closer to the viewer, but the character always runs in front of. And then generally the foreground layer where the player character runs ahead. And you will get all of the assets that you need to render and you will draw them back to front. Because our background is one big image, we're just really laying game entities on top of an image. And we've got a bit of a Z-index system, so there's a couple of things that we put in the scene, like bottles of jam that you can run in front of, and a couple of other assets that are cool. So you can see an example of the way our items are overlaid here with this slightly translucent jug. And I'll show you the game running in a bit, and you'll kind of see this all folded down in these 2 perspectives. So for this game, we implemented a super lo-fi camera that worked out what to draw in our canvas based on the player's position in the world, and it basically just scrolls the background and all of the assets left and right. And the player character never really goes anything at all. Never really goes anywhere at all, and the illusion is maintained. The other thing that it has to do, though, is when you start at the leftmost edge of the screen and the rightmost edge of the screen, actually has to finally move that player sprite. So we have this tiny kind of to canvas position class to convert all of our sprite locations to where they should be rendered. And obviously anything that's rendered off the minus axis on the left or off the width of the canvas just disappears. Now, traditional 2D games are often made up of tile sets and level data. And the idea is like old systems didn't necessarily have the amount of memory to have these big JPEGs stored in memory. So you would have repeating tiles that would have different attributes associated with them. And the level data would just really be a pointer to that little chunk of level. And they were tiled across the screen. Now, frequently those level tiles would be things like they would be passable or destructible or solid. When rendered. Now, it's good for memory efficiency because, you know, we're blessed with modern hardware today. Our whole JPEG's 130 kilobytes, so I decided to not do any performance optimization to that. I don't think I could improve on the JPEG standard. So in this 2D engine, we're using something called bounded box collision. And collision detection is very, very complicated in different kinds of game engines, but in 2D it's quite simple. Now, each of our entities has this box drawn around it with various collision points like we talked about before. So we have a line of collision points at the bottom, one in the center, some around the corners, and we can set up where we want the collision points to be. So it's not always the square box that's colliding, and you can have odd-shaped objects. Now, this is relatively inexpensive because as the game ticks, the player character just checks if any of its specific points are colliding with the environment. And we make this even cheaper by using those hotspots around our box, so for instance the 4 corners, and we just check if they've crossed over the coordinates of each other to see if those boxes are intersecting. So if you've ever used an engine like Unity, and you might have heard the collision detection routines called box colliders, or the wonderfully opaque AABB, which stands for axis-aligned bounding boxes. Wonderful. That's kind of the collision detection used in a lot of simple 3D games. So we're using this fun little hack for level geometry in our game for collision detection. So we have this second image that matches exactly our level in dimensions. And we just painted it in black and white. Brilliant hack. So we use the colors of specific parts of the level to determine if terrain is solid, if it'll kill you, all the scary red stuff, or if it's the end target goal, the green stuff. So this is really, really easy to do in the browser because the native APIs support this trivially. We're just loading the collision map JPEG in an invisible canvas, and we know that our player location is going to be the same in the world as it is on the collision map. And we just use the getImageData API with the XY coordinates to pluck out the color of each of our collision points and check if we can move or not. So pretty simple. If you had a drastically larger level, this approach would be probably not very scalable. But for levels that are like a minute or 2 long, actually, it's a really simple and intuitive way to encode this data that's really easy to edit. And a lot of the things that you get with modern game engines are easy editors, and all I have is paint. So the collision detection code in this version of our game engine just scans downward to find the black color to determine if we're on the solid ground, if you're in a passable state. Otherwise, our characters can move freely. So our enemy collision mostly works based on those hotspots, and this is a debug mode that I built into the engine. I think the easiest way to understand it is just to see it running. And the Jam game contains this view where we just render the collision points in red on the UI. Now, this technique allows us to make sure that we can get some nice game feel. You could see that actually, if I realize I need to go back again to make that play, you'll notice actually we're only really checking the floor and the center point, right? And it means that that box, when it jumps over that weird boxy mouse, doesn't die if he lands on the back half of the mouse as it's running away. Because if every time you clip the edge, it would feel horrible. So a lot of 2D platform game feel is a combination of the way that your physics feel and the sensitivity and forgiveness baked into your collision detection. You'll find lots and lots of 2D games especially that do things like if you think you missed that jump, no you didn't. No you didn't. If you were about 5 pixels away, you definitely made that jump. Don't worry about it. Right? And that makes games feel good. Now, our code to deal with the player death exists in the update function of our enemy entity, actually. So every time the enemy updates, it just checks who it's colliding with, and if it happens to be the player, and the player happens to be alive, it'll find that behavior of killable and say, hey, killable behavior, execute. And what that does is it sets the state to dead on the player and ends the game. You can implement all sorts of different entity interactions in the same manner, and that's why having characteristics is really useful, because you can generalize that stuff and not have to write like a killable player, a killable enemy, 10 different variations of the killable enemy, etc. Let's talk about AI. So AI use in games is a huge and vast topic that covers multiple different approaches and programming styles here that would be impossible to dent in a couple of slides. Now, the way it's triggered, however, is generally consistent with all the other game loop-driven updates in the game. So every nth tick, the AI for each entity, or the AI subsystem processing the game data, if you're doing an ECS-based system, executes some logic and makes our players do something. Now, these are some great examples of games with drastically different approaches to AI. So most games have some kind of pathfinding AI, using either something called navigation meshes, which imagine invisible roads across the game world, or common algorithms like A-star pathfinding. And then they have a bunch of other series of techniques layered on top of navigation to help the entities choose what they do. So games like Halo popularize using something called behavior trees, where characters have sets of actions that they can pick from, while Gope goal-oriented action planning is really popular in games with kind of emergent gameplay systems where entities are given a goal and a set of actions that they can perform along with tests to see if they're getting closer. Probably first popularized by the game Fear, where they had AI agents that got given actions to hunt the player. The games of the late 90s were really big on experimenting with neural networks. So Creatures and Black and White on here used neural networks. Games like Doom and Half-Life used finite state machines, which actually continues to be a pretty popular approach. And then finally, a bunch of kind of more hybrid AI approaches. So you've got games like Left 4 Dead, where they had regular NPC AI, but they also had an AI director that not only controlled the enemies, but it also had like a state machine where it monitored how active the player was and how stressful the game was for the player, and would ratchet up intensity up and down if the player wasn't doing much, right? So it's kind of competing AIs in the same game world. So if you're interested in deep dives about different AI techniques, there's a really brilliant kind of Substack and YouTube called AI in Games. Loads and loads of real deep dive videos into all these different kinds of systems. Absolutely recommendation. However, for completeness sake, I want us to take a quick look at the AI in IMJam. So the AI in IMJam, it runs from left to right and attempts not to fall off cliffs. Stunning. I mean, to be fair, me too. So our simple AI just gives the enemy an X velocity of 4 pixels per tick in whatever direction it's facing when it's spawned, and every tick, the enemy AI looks ahead and says, am I about to fall to my death off a cliff? If the answer is yes, it turns around. It also checks if it's stuck, right? So if it's collided with a wall, by checking if its current X location is the same as the one it was at in its last tick. And if it's hit a wall, it turns around. This means our AI basically will just run backwards and forwards along any platform it spawns on, but won't fall into the pits and kills itself, which is what the first version of the AI definitely did all the time. So originally I'd written this really aggressive AI that made use of this cool-off counter that you can see remnants of on like the third line of code there. And the gameplay experience was distinctly unfun, because if you ever stopped moving for more than about 100 milliseconds, the mouse would turn around and hunt you down, and you could not escape them. It was just like a furious speed run through the match. So I thought this is a really good example of having to actually tune the AI to be dumber to make the game more fun. And I promise you, every video game you ever play has its AI tuned to be dumber to make it fun for you. There's lots of excellent examples of how, like, for instance, in the game BioShock, the first shot that an AI enemy takes at you will always miss, because it's no fun to be shot in the back by something you didn't see. So, can't really do a whole talk about building games without letting you play one. So I've made a single-player version of the IMJam game where you can race against your own ghosts. Hopefully this will work if you try it now. It should work on your phones with touch input. I'll let you work out the controls. Or with controllers if you plug an Xbox gamepad in, or with a mouse and keyboard. I'm kind of super proud about how fun this quick little game turned out, especially given the incredible artwork, and actually people loved it at the event that it was in. So I'm going to try. I don't know whether I'm going to be able to play this here on the screen, just for the sake of completeness. Jam. There we go. It does in fact work now. You can see here, we can do this. Oh, my mouse cursor is a long way away. I'm going to die. There's some other cool bits of AI in here, right? So as we run here, there's a really tricky jump here that's really twitchy. This piece of toast is AI that tries to detect the player and jumps when you're nearby. And then finally, if I can still do this, I can make it all the way over here. No. And hopefully, God, I'm really, really bad at this when I'm playing a monitor by my feet. And I can become Jam. So there's a huge amount of game engines out there. Why did I build this? You know what? I think if you're going to build a game tomorrow, just use Godot or Unity or Unreal or something, honestly. And there's about 100 JavaScript game engines that'll take care of a lot of the rendering code for you that we've gone through in this. But I think if you want to really be serious about making games, it's good to understand the primitive kind of data structures and the way you should structure an engine to make this stuff work. So I thought it was really fun, and given that this is more of a developer festival, less of a conference, we should do some fun stuff occasionally. But yes, please choose prior art generally. I hope you've had fun with this. I hope this has been interesting, and I hope you've been a bit inspired to go and make your own toys. It's fun to program for not money. So yeah, please have a fun rest of the conference. If I see you around, I'd love to hang out. I wrote a kid's book about building games for 10-year-old me. That was the book I wanted when I was 10. You can buy it where books are sold. Follow me on socials, blah, blah, blah. It's my birthday in 2 days, so if you bring me a shot, I'll drink it. It's a challenge. This is how I die. Thanks, everyone. Really appreciate it.